the cloud. Good to go.
All right. Hi, everyone. Let's start the afternoon session. So our first speaker is Giulio Biroli. He is a physics professor in École Normale Supérieure. And his field is statistical physics of disordered systems in general. And then lately he has been working on machine learning and theoretical ecology.
Right.
And I think you need to.
Yes, I will do it. But so I just a disclaimer. So I wanted to speak about randomization group and machine learning, but then I realized after Aurelian introduction that it was a little bit off topic, I think. And probably for you, it's better that I speak about some older stuff about landscape dynamics in high dimensional problem, how you find minima, how you characterize landscape. So sorry, I mean, of course, if you want to know more about randomization group, this is a machine learning. This is what I'm doing now. So you are welcome to ask me more later. So I'm going to do what I shouldn't do, which means changing talk in the just in the morning to adapt to the crowd. So this is what I want to talk about. I think it's interesting with some of the work that has been already discussed and others that will be discussed later. All right, so the idea is that actually many high-dimensional problems related to inference and machine learning. For example, if you have a signal that you have to retrieve in presence of noise, if you have one particular minimum that you have to retrieve in a very complex high-dimensional landscape, and in general you do it minimizing some energy function or some empirical loss on some cost function, then it's interesting to study the dynamics of the landscape as was discussed. In general, people use local optimization algorithms. So in this talk, will be just gradient descent or gradient flow. And in many cases, actually, that has been studied in quite in detail, you have, depending on, let's say, signal to noise ratio, let's say the amount of noise or the amount of data that you have in many cases, different regime. The regime in which is impossible to find the, let's say, the good minima or the signal. Then there is a regime in which is hard, which means that, here it depends on the algorithm, whether you are able to do it or not, but typically there is a regime in which people think that maybe any algorithm will take exponential n, where n is the dimension is the number of degrees of freedom. And then there is a regime which is easy, and now this threshold here is the algorithmic threshold. Of course, it depends on the algorithm, so or your optimization method. So, well, I think many questions in this context are, well, if you have a landscape, if you have an energy that you want to minimize, then you can study the landscape, how the property of the landscape can tell you something about the dynamics, which is in principle non-trivial. And do you need to have a landscape which is trivial in order to be able to retrieve the signal or to find a good minima? Or no, you can have a lot of bad minima and still finding the good minima. There is no problem. And more generally, how the landscape influences the dynamics. Now there is a, let's say this again, beware. So what I'm going to tell you today is much more applicable to problem of inference and optimization problems. And I think problems related to artificial neural network have much more, let's say, other stuff that one has to consider. In particular, in many cases in artificial neural network, one is an over-parameterized regime in which the landscape probably is quite flat. And oops, sorry. Okay. All right. So you are in this regime in which the landscape is flat, and moreover, what you really want to minimize is not the train loss, but it's the test loss. So there is clearly a new ingredient in the case of artificial neural network. But still, I mean, some of the questions: how the landscape influences the dynamics, what is the role of good minima versus bad minima, and where is the algorithmic threshold, are things that at least you can start to learn in these kind of problems. Then artificial neural network are more difficult, and let's say it's the future. All right, so sorry. I want to be concrete and really go through a case which is simple enough, even though it's still quite complex, that we have studied in detail. Is what is called the case of high-dimensional inference problem, in which it's called a spike matrix tensor problem. So it's a generalization of PCA, matrix CCA. So what you get in this case is that you have a signal. So the signal is an n-dimensional vector, xi star. And then what you get Actually, you don't get the vector. What you receive a matrix which is formed from this vector in this way. So you take, you construct the matrix like this, multiplying xi by j, and then this is corrupted by noise. So you get a corrupted version, not of the vector, but of the matrix which is produced by the vector, and with certain noise, which is certain strength delta 2. And then if the problem was only this one, this would be called the problem of just PCA. And what you would like to know is, depending on the strength of the noise, when you are able to retrieve or not the information, which is x star. Now imagine that you get this, and then you get also a tensor version. So you create a tensor from x star, again you get noise, what you get is t, and from t you want to retrieve what is x star. So this is what is called the spike matrix tensor problem. And it has been, I think, introduced, the tensor problem has been introduced by Montalano and Richard in 2014. Now, in this case, if I want to prove, you can do smart things in this case, but we are not doing a smart approach. So we are not going to do a bias optimal estimation, which would be the best thing we could do. We are going to proceed in a way in which we would proceed for example, in artificial neural network. So you want to define an energy function, and then you want to minimize it using a very simple algorithm. So here is not, the aim is not to find a smart algorithm to solve this problem. There are, and this gradient descent is not one of them. What we want to understand is how the gradient descent behaves in this case, in which we will really study the dynamics and the landscape, even if it's a high-dimensional problem with a very complicated, complex landscape. So the energy that you decide to study is this one. So this is the energy that you get naturally if you study the bias optimal, you do the bias optimal estimation. So in the bias optimal estimation, the probability of x, so of the so this is the estimation of the signal, will be given by exponential minus certain energy, and this is the energy that you get. So it's not completely, if you are not used to bias optimal estimation, maybe it's not easy to see. But one way to think about it is that if you know that Yij is a kind of, it's constructed by Xi star, Xj star. So you could think that one way to estimate, to have an estimation of what is X, is you take Yj, you subtract Xi and J, then you take the square and try to minimize it. Since here you have information about Y and by T, you construct this mean square loss with some weight in front. And now the weights here are put in such a way are the ones which come from the bias optimal estimation. Yeah.
So Xi, Xj, and Xi1, Xip are different objects, right?
Sorry, say again.
So Xi, Xj, and Xi1.
Yes.
So they are completely different.
Completely. So this is the signal that in principle I don't know. And X is the variable.
There's also the signal in the T, right? So
Exactly.
T is X star and
These are
X star.
the same.
And they are the same.
Yes. Yeah. Okay, so what we're going to do is we are going to minimize this energy function. That's our cost function. And so in this case, now we have a problem, which is a high-dimensional problem, in which there is a landscape is defined by this energy function. X is a vector in n dimension when n goes to infinity. And we have a dynamics. We consider gradient flow, and we can consider also gradient descent. We consider gradient flow in the positive. And the nice thing about this is that you can really study completely the property of the landscape. So this is through the Katzreis method that was actually cited in the introduction. So this is a method to compute the number of critical points has been developed for Gaussian random function, and then has been extended actually to functions which are non-Gaussian quite recently. And so what happens in this case is that indeed you have a complicated landscape in the sense that the number of critical points here scales like exponential of n is the number of variables times sigma, and sigma is what we call the complexity. So you have a very large number of critical points. You can compute the number of critical points at a given energy, so you fix the energy and between energy E and E plus E, you can compute the number of critical points. If you want, you can compute the number of minima, or you can compute the number of critical points with a given index, which means a certain number of positive and negative direction. So first, the nice thing about this is that it has been developed in a completely rigorous way in its annealed version, in the sense that you compute the average of the number of critical points. However, for people working in this order system, they know that this is not what you should compute. What you should compute is the typical number, and to get the typical number, you have to compute the average of the logarithm of n. This will give you the sigma here for a given sample. Okay, so this is something that you can do with replicas as we did it in this paper.
Can you explain what is the typical one? Like, once I have the expectation, can I not just use some sort of concentration to like, what is special about the law?
It's just because this one is actually, you shouldn't compute the average, because the fact that since n is the scale like exponential of n sigma,
Oh, I see.
but then you have a probability which of having rare sample which goes exponential minus n, so this is why. Okay, all right. So this we can do it. So in this model, we can use this method and characterize completely the landscape, computing this exponential number of critical points and minima. We can also study the dynamics. So the dynamics in very high dimension is a complicated thing to study, but this can be done using results from all results from spin-glass theory. So I'm not going through derivation or even the explaining really in detail. The only thing I want to say is that you can obtain integral differential equation, which is a kind of mean field, dynamical mean field equation, in which you have the correlation function. So this is CTT prime is the correlation between the state of the system at time t and the state of the system at t prime. And these are other objects that comes. And I mean, this is a closed set of equation that you can solve, and you will describe the dynamics in large dimension at any finite time. So this is just to say that we can then study when gradient descent will be able to retrieve the signal, or when gradient descent is not able to retrieve the signal. And then we can study the landscape, and then we can try to see, well, how we can connect landscape properties to dynamics. Okay, so here just to go directly to the result. So what you have here is, well, here you have this parameter, delta 2 and delta p. Well, what you have to think is, again, just going a bit quickly, is that in this regime, so this is the regime of low noise, this is the regime of strong noise. What you see here is that this line here is what you can compute, and you know that in this regime here, the landscape is easy. There is just one minimum, one global minimum, or if there is a symmetry, there will be two global minimum. So the landscape here is what we call trivial, and this is what is called trivialization transition. Below this, there is an exponential number of minimum. There is the good one, but there is an exponential number of bad ones. And this line that you find here is the one that you find from the dynamics. So gradient descent or gradient flow actually will be able to retrieve the signal if you're above this line. So in this regime, actually gradient flow and gradient descent are able to retrieve the signal even if there is an exponential number of bad minimum. And then here gradient descent fail, and in this regime, actually, in this regime, you can find algorithms that we are not going to fail, they are going to go through the signal. Yeah.
So, and I think I missed what was delta p. I mean, you mentioned it's related to noise, but I don't know if I got the definition.
So delta p is the strength of the noise that is added to the transfer part. So let me.
Okay.
So this is the strength of this, and delta 2 is the strength of this.
Okay, so the two things you're doing on the two axes is delta p and the delta 2. Okay.
Yeah.
Can I ask a question?
Yeah.
So in case like when there are exponentially many local minima and gradient descent succeeds, is it clear like why this is the case? I mean, like I'm guessing they are not isolated.
They are not
Isolated local minima for the like if otherwise like if gradient descent. Okay, so
They are
isolated.
Yeah.
So okay, how come gradient descent is able to like avoid this?
Exactly. That's the purpose of my so let's discover how this is possible. And I think this is the magic of high dimension. So one talks a lot about the curse of high dimension, but this is actually the miracle of high dimension. So in low dimension, if you have that minima, if you start from a random initial condition, well, some fraction of cases you get them. Here you have an exponential number of that minima, but if you start from random initial condition, you never get to them. So how this is possible? This is the what I wanted to show you is, so first, okay, this is an illustration and a caricature of the landscape in terms of minima. So of course we can do computation, but it's just to illustrate what's happening. R is the strength, is the signal to noise ratio. So when I move this way, I get lower and lower noise. And here, so you have to think that, so here X is on the sphere, because, well, we take it on the sphere, because the signal X star is on the sphere. And then in this direction would be the direction in which there is the signal. Since you are in high dimension, the majority actually of configuration are around the equator, are orthogonal to the signal, because you will have an exponential number of configuration. And here what you get is that you have a band, so there is the signal here, and there is a band of exponential number of minima, which are bad minima, in principle, because they are not related to the signal, if the noise is not too strong. And so the yellow one here is where the ground state is. So if this noise is very strong, there is a signal, but the ground state has nothing to do with the signal. At a certain point, actually, this yellow thing is the ground state start to be in the direction of the signal. So I mean, the signal is here, and you don't have a perfect overlap with the signal, but the ground state starts to point in the direction of the signal. But the largest number of minima are here. So you have an exponential number of bad minima here, and you have a ground state which is here, which points in the direction of the signal. And then you increase more and more. At a certain point, you get just two global minima by symmetry, and nothing else, no bad minima. And to understand indeed why the system is not trapped why gradient descent is not trapped by the bad minima, you should understand actually how is the characterization of the minima in the landscape. So what you have, if you look in energy, is that at very high energy, you don't have bad minima, you just have solvers. Then when you go down in energy, you start to have a lot of minima, which are actually called marginally stable, in the sense that you can compute the density of eigenvalues of their Hessian. And in the simple model, it's a random matrix that one can solve. It's the Wigner semicircle that just touch zero. So these are the highest bad minima. Then you go down, and so you have minima which are less numerous, still exponential, but less numerous, and they are more and more stable. So their density of eigenvalues is pushed toward the left. Okay, so this is how you find minima, exponential number. Here there are the marginal one, and then you go down, they are more and more stable. Now,
I know those who are looking at these models. You mentioned spike models. Usually, there's a spike that we get out of the bug once the noise is strong enough.
yes.
So why is it not showing here?
No, this is just because, sorry, you're right. It's just because I'm considering, for the moment, I'm considering noise strong, and now I'm coming exactly your point. So just one slide of patience. So here is showing the dynamics. So let's consider the case in which the dynamics is not able to achieve the signal. So here you can solve the dynamics exactly, analyzing or solving this integral differential equation. This is the energy, and here what you see is really the transition. So here the system is stuck, and it becomes so it's not able to find the ground state which points in the direction of the signal. And where is it stuck? It's stuck in the minima, which are the highest one, the more numerous, and the less stable. So because probably they have a very large Bayesian attraction. And then at a certain point, actually, you see that is where the transition of gradient descent happened. The system seems to go toward this minima, but at a certain point, they realize that there is a one direction, some way to escape, and then the energy goes down, and here actually it becomes oriented in the direction of the signal. So now the question is, what is this transition? Yeah. So now the question is, what is this transition? This is related to what Oriana was saying. So what you can study is you can study the Hessian indeed of the states that trap the dynamics. And what you see is that as long as the system is below the algorithmic threshold, so if the noise is too strong, while you have a certain, the Hessian, first thing, the Hessian is always at this form, a kind of G matrix, and then you have a correction which is a spike term. So now this kind of correction is known that is produced actually an eigenvalue that pops out of the semicircle. And so in this case, what happens is that all this kind of matrix, because of this, these are the Hessian of the critical points, we have one eigenvalue that will pop out. Now you can understand what's going to happen is that the dynamics is trapped in these high energy states. And at a certain point, the noise is not too strong. And there is one eigenvalue that pops out. And this eigenvalue has an eigenvector, which is in the direction of the signal. So what happened in here, what you should think is that gradient descent goes down. If the noise is too strong, it gets trapped in this exponential number of bad marginal stable minima. And then when you decrease the noise, this marginal stable minima will become unstable because they have a direction toward the signal. So the system will go down and then will surf toward the signal. And it will do this. And actually, even though below there is an exponential number of stable minima, but we will never see that because actually it never get to them because we get to this one, which has the largest Bayesian attraction, which attracts actually the dynamics with probability 1 in the large dimension. And then once it's attracted there, then the system flow to the solution. Yeah.
I have a question. How are you sure that you get finite kind of convergence, the linear saddle point, and it becomes like you have an escape direction that is like this, like in this transition phase that you saw, like it becomes at the border very difficult to bring this to find.
So I'm sure that so in principle, I can solve the dynamics at infinite time, and I can compute the action. So this is let's say a nice case in which you can really do everything. So it's true that once if you go closer to the algorithmic threshold, closer probably of scale 1/n, then maybe it will take a time which is, I don't know which scale with n to escape. But if you are, let's say, below this, you won't, and if you are above this, you will escape on time which are more than 1.
Okay, thank you.
I have also a question about, you made a statement of biases of attractions. I wonder if this is something you can critically understand. But my understanding is characterized with the critical points.
Yeah.
What do you, is there a way to characterize the size of these biases of attraction?
So no, the reality is that no. So in this, it's a very interesting question, but it's a very difficult one. So in this case, the thing is that we can compute with Katz-Rice what are the minima. We have the dynamics, and so then, I mean, it's almost tautology if we know that the dynamics goes there. But if you say, can I have a way to compute Bayesian of attraction without doing the dynamics? I don't know how to do it, even though it would be very, very interesting. Okay, so this is, I mean, the reason, well, this was a little video to show you this is the action that the system sees while it's going down. So you see, you start with many directions in which you can escape because, well, the system starts from random initial condition. Then you go closer to this almost marginal points, and this is the spike actually. And what you see is that N is the overlap with the signal. So you have a long phase in which nothing happens, and then actually then the system will start to move. You will start orienting the direction of the signal, and this is precisely actually where the system starts to go down in the direction of the spike. So this is what you will see. Just a moment. Takes a long time. Okay, so while it's here, you see that it went a little bit away, and then it goes to the overlap here, obviously with the signal. Yeah.
So zero, like that number on the y-axis, I think is the angle, or
yeah, it's the angle. Yeah, it's the overlap. It's
so
really...
that it never becomes 1. So
no, it never becomes 1. Yeah, because actually the disorder in this case is such that it deforms actually the ground state. You really must have almost, yeah. It's really, you do what is called weak recovery, not strong recovery. All right, so here now, this line that you have here is the line that we can compute analytically just to studying the random matrix theory problem. So we just study what are the bad minima that trap gradient descent, and we study when they have a direction which start to appear in the direction of the signal. And this gives us this line, which coincides actually with the result from the dynamics that we have before. Okay, so well, just to summarize, here the picture is this one. So in this case, is that you have an hard phase. In this hard phase, you have a lot of, let's say, bad minima. You have a good one, which is here. But if you do gradient descent, you will be trapped around here. These are the marginal states, which are very exponential numerals. Then at a certain point, gradient descent is able, actually, this is the easy phase for gradient descent, because the system actually goes here and then goes to this minimum, even though there is an exponential number of bad minima that the system never sees. And then only later, actually, here, the landscape becomes simple. So there are no more bad minima whatsoever. Yes.
Can you remind me what SNR is?
Sorry, this is the signal to noise ratio. Is roughly is 1 over the amount of noise that I'm putting in the corrupting the signal.
Do you think perhaps that one could also probably noise insert noise in the algorithm in some sense? Maybe a bit like what Giulio presented, that one can inject noise that one can think of it of like a convolving landscape randomly or something.
Yes, I think it's interesting. So I don't know whether that noise one would put it on this axis, but I think one could study this problem injecting that.
Because if one could, maybe this could be used as a attempt to explain why the randomness in stochastic way in the sense of it's for.
Yeah, yeah. So I think,
The main idea.
yeah, I think it can be done using these techniques. I know that someone actually did, it's completely unrelated, it's a different idea, but in physics, people starting to study what is called active matter, in which you have noise, that rectangular time translation, so time reversal. And it's known that in the physical system, if you have a glass, and you take a noise, glass means particle that moves very slowly, you put a noise which is different from the usual noise. It's a noise which is not time reversal invariant. Actually, you can speed up a lot the dynamics. So people are currently trying to apply to this model. It seems to actually to work, to give rise to a better algorithmic threshold. So this is the first. Thing is, in this case, you can understand why the gradient descent succeed even in present exponential numbers for this minima. And by the way, it's known actually that in deep nets, I mean, there are examples in which, well, you never saw them, but they are there. So there is a nice work actually by you task and another one. Okay, and then the other thing is, I mean, at least in this simple case, the algorithmic threshold, you can really understand it as you look for what are the minima that trap the signal, and you look at the random matrix theory problem that tells you when there is a direction that toward the signal that emerges. And so I will conclude, I think, with this, and with conjecture and extension. So the conjecture is that for many problems in which you have to recover a signal, or you have to do weak recovery, so maybe the gradient descent threshold can be really understood in this way. You study where there are the minima that trap the signal, and then you solve the random matrix theory problems associated with it, in which you have to study when there is a direct eigenvalues which correspond to an eigenvector in the direction of the signal that appears. And so this is a conjecture in a sense. So when we went to we studied more complicated case like generalized linear model. So loss function, which now looks more like a machine learning problem, in which you have a signal x star to retrieve, you have a certain measurement vector. This is the sum over mu, and this is the loss function that you minimize. So for example, if you take a v, which is like this, it's called a phase retrieval problem. In principle, for generalized linear model now, we can apply the Katsura's method. So and this is what I was saying before. Katsura's method was developed a lot for Gaussian random function. Here the function is random, but it's not Gaussian. But still we can do it, and so we did it in this paper. But we still didn't completely analyze the landscape from this point of view. But the methodology now is there. We can also study the dynamics with dynamical mutual theory. So in principle, for all these types of model, we can really test this conjecture. So for the moment, we need a shortcut. And the shortcut is, on the one hand, simulate the model, the dynamics of the model, and on the other hand, just study directly the random matrix theory problem. This is what we did in this work, and then we are also doing for other models more recently. And it seems really to work. It seems that indeed is the transition, which is called the BBP, in which there is a spike that comes out that is related for the algorithmic threshold of the gradient descent. And then, I'm sorry if I skip many references because I prefer this talk in rush, trying to change from the previous one. So if I didn't cite people should cite, I apologize. I add something which is a little bit, so it's not exactly related to what I did, but there are some recent nice rigorous results for online SGD by Benarus, Desari, and Jagannath, in which, I mean, there is a scenario which is similar to what I discussed, but it's for online SGD, so it's a different kind of dynamics, and it's not exactly the same kind of model, but it's related, and so I think it's a nice reference report. So thank you very much.
Any questions, Giulio?
But I'm wondering here, like you have these sort of square functions when for the phase retrieval. One thing I wasn't sure with Katsura is that if this could be used to analyze let's say you have a function of a neural network of arbitrary nonlinear functions, or even like a ring or something like this. So here, I guess it looks like you have some quadratic activation function in some sense.
Yeah.
I wonder how difficult that is to analyze, because I guess with Katsura, from my understanding, you have the determinant of the Hessian that shows up. So, and I think when you have this nonlinear activation, it's really not super easy to understand what the spectrum is. But this big neuron. So can you maybe comment on on this, like for how it is to do this analysis, whether it could be generalized to other types of non-activation mechanisms.
So yeah, you can do it with any kind of, at least this is just, let's say it's a one node neural network. For one node neural network can take any kind of D, and one is able to study it. And the reason is that if you consider the Hessian, which comes in the problem of the determinant, the Hessian would be sum over mu, and then you will have things like sin mu, and then a function, and then this derivative of this function. And these are kind of deformed initial matrices that one is able to do.
You can see that now.
Yeah, and I think it's, if you consider a finite number of neurons, you can still do it. If you want to do one in the million, I don't know what you have to do.
Can I have like a comment slash question? So like in this last paper you mentioned, the authors are considering the single index model and then try to learn it by using a neural network and introduce like a thing called information exponent, which is the complexity of the activation function, essentially how nonlinear it is. And then depending on the complexity, they can still recover the signal.
Okay.
If I remember.
Yeah.
Any other questions?
And maybe another one, but a lot of the things we discussed is for gradient descent. So this morning we're talking about adaptive methods of other sort of optimizers. Is there a way to, or can you analyze other dynamics like gradient descent?
Yes, so it's not something I did, it's something that actually Stefano Sarao and Francesco Urbani did. Yes, they used, I think, Nesterov and Polia, they did that.
Okay.
I think, I don't remember if it was for this model or another one, but yes, you can do it. It's actually,
are the results any different or like are there some
not remember. I can give you the reference.
okay, yeah.
One last question. Let's thank Giulio again.